All right, ladies and gentlemen, boys and girls, welcome back. Today we're going to talk about atomic mass. All right, so this video is going to talk about what is atomic mass, how it's different than mass number, and answering our most important question that we're going to really hit on today. And that question is, why is the atomic mass a decimal? All right, so if you look at your periodic table, we have our atomic number at the top, right, which tells us the number of protons, right? And then we have the number at the bottom, which is a decimal. Early in the year, we talked a lot about the mass number, which is rounding that number. Right? For example, oxygen, it's listed as 15.99. We would say 16. That's the mass number. That's the number we used. All right? But why is oxygen listed at 15.99? Why isn't it just 16? All right? That's going to be our topic today. And the short answer is going to be because of isotopes. All right, but we're going to come back at the very end of at the end of this video. We're going to come back and answer this question about why is it a decimal. All right, so a big part of it, as I just said, has to do with the idea that there are isotopes. There is not just one version of each element. I should say the vast majority of them. There are multiple versions based on different amounts of mass, and so we're just going to look at an example of one of them here, and we're going to look about why. We'll pick the element boron. Why boron, all right, has a decimal as its atomic mass, and it has to do with the idea that there's multiple versions or different isotopes. So we look at the periodic table, right? So if we want to look at boron, by the way, if you don't have out your handy dandy notebooks, you should have them out right now. All right, let's do some notes here. Let's talk a little bit about boron's atomic mass. So we know boron, when we look at the periodic table, boron has a mass number of 11. And the reason why it has a mass number of 11 is because we take that boron's atomic mass which is 10.812. So why is it 10.812? The short answer a lot of people want to give is, well, what about electrons, right? Is it because the extra mass of the electrons? The answer is no, because remember that electron mass is so negligible. It's so small that it would not even register. It would be to the decimal place way over here, not making an impact, right? We can't have an eighth of a proton or a 0.8 of a neutron. And because they're the fundamental particles. So why do we get this number? All right. The answer is to do with isotopes. So for example, I'm going to pick boron just because it's a pretty simple one to talk about here. Let's talk about, there are 13 different versions of boron, 13 isotopes. I'm just going to pick kind of 3 most abundant. All right. So there's boron 9. There's boron 10. And there's boron 11. All right. Boron 9, boron 10, boron 11. So we have the element for each one of them, all borons, but we have different masses, right? A mass of 9 AMU, 10 AMU, and 11 AMU. All right. We get that AMU because boron is going to have 5 protons for each one of them, same number of protons for each isotope, but the difference is the number of neutrons. This one has a mass of 9 AMU, 5 of them are protons. That means 4 of them are neutrons. So that means this one has 5 neutrons. This one has 6 neutrons. This should be a review up to this point. All right. We know that they're different masses. Now, this one has the most neutrons, medium, and this one has the less. Now, actually, this one right here, boron 9, is radioactive, which we just recently spoke about. That means it has an unstable. See how it has very few neutrons? That means it has a lower amount of strong nuclear force that's holding those protons together. This one will eventually decay and fall apart. All right. Because of that, there's not that much boron 9 in the universe, or at least as far as we found. All right. So we have 3 different isotopes of boron. All right. There are 13 different ones. These are just the 3 most popular or most abundant, the ones we find the most. All right. So if I was going to pick one number to put on the periodic table, should I, because I want to label the mass, periodic table gives us information about each element. Should I put a 9? Should I put a 10? Or should I put 11? All right. Well, instinctively, people might say, well, okay, since I only can put one number, I don't want to put every version of boron on the periodic table. Why don't I just put 10? Because it's right in the middle. And I get it. Like, you would want to average it, right? One, it's in the middle, or I could average it, 9 plus 10 plus 11 is 30, divided by 3, that's 10. That's an average, right? But there's something we're missing here, all right? And it has to do with the word I keep saying, and that is the word abundance, all right? Although all of these can be found, if I were to take all the boron that we've ever sampled in the world, 80% of that boron, right, is boron 11. It's a very stable version of boron. And about 19% of it is boron 10. And only about 0.05% of it is boron 9. The other 0.05% is split up among the other 10 different radioactive isotopes. So now I see this, okay, I'm going to have to pick a number to put on here. An average is a good idea, but at the same time, notice that this average isn't split right down the middle. There is so much boron 11, which means if I'm doing an experiment and I need to find out a mass, more often than not, I'm using boron 11 just because there's so much more of it. So now I need to take into consideration not just maybe picking an average mass to put on the periodic table, but doing it by the amount of the abundance of each one, right? So think of this as like taking a test, right? If I take one test that's worth 5 points, and I take another test that's 10 points, and I take another test that's 150 points, right? My final score is going to be way more skewed by the one that is much larger, all right? My final score is going to depend on that big one here. Another way to think about this here, to kind of help you think about it, is if this was almost like a little numbered line in math class, just kind of doing this a little here on the side. Right? So if I have, boron 9, boron 10, and boron 11, or if I'm thinking this in terms of the amount of abundance, there's very little boron 9 in the world. There's a little bit more boron 10 in the world, right? And there's a whole lot of boron 11 in the world. If I was going to say what is the average in this case here, it's not going to be right in the middle because look how much there is of this very specific isotope. There's a lot more boron 11. So if I was going to say the average on this number line, it's not between just 9 and 10 right here because it's weighted by abundance. All right. So my average is not going to be here. My average is going to be much closer to 11. Not exactly 11 because there's still 9 and 10 that are weighing it down, kind of weighing it. But notice that it's going to pull it down a little bit further. So I was going to take the average of these here of 9, 10, and 11 by abundance. Right? There's a mathematical formula to do that. All right, we would end up getting 10.182 AMU. That is the atomic mass, the kind of the average mass that we use for boron because there are different isotopes, but each isotope has a different amount of abundance or how much of it there is. Okay, so we had to think about that in a little bit in terms of math here, all right? And so let's go back to our original question. We talked about isotopes here, we talked about mass, we talked about AMUs, protons, neutrons. Now we come back to the question that we started with here. Why is the atomic mass a decimal? All right, it is decimal because we need to have an average mass of all the isotopes, but we have to include not just the average, all right, not just a straight up average. We have to include about how much of each one there is. All right. So to kind of summarize it, why is the atomic mass a decimal? It's because it is the average mass of the isotopes by abundance. Right? Abundance means like how much of it there is. Right? Since there is the average mass of 9, 10, and 11, but we have to add to it this idea of 5. Because there is more of 11, it gets a greater weight to it, and it shifts that average not to 10, but closer to 11, or to about 10.8. So we shifted it between 10 and 11, but not 10.5. It's closer to 11 at 10.8 because of all that abundance of boron 11. All right, so there was our question. That's kind of the basics of the atomic mass. All right, if there's any parts of this you got confused about, or it went too fast, you need to rethink about, maybe you're writing it down, but you weren't really listening, don't hesitate to go back on this video. All right, otherwise, thank you guys very much, and good luck, and may the science be with you.